Hey, in today's video we will define negative topological cyclic homology, or TC-, by taking homotopy fixed points with respect to the S1 action on THH that we constructed recently. So we will see what this has to do with HC-, which we defined in terms of certain X groups way back when we discussed classical Hochschild homology. And we will also compute TC- in the case of HFP. And for that, we will also see the main tool that's used to accomplish this, called the homotopy fixed point spectral sequence. I'm Achim Krause from Mathematics Münster. So, with the circle action on topological Hochschild homology that we defined in the previous video, or one of the previous videos, we can now define what's called negative topological cyclic homology, or TC-, simply as the homotopy fixed points of the S1 action. So if you recall, when we talked about S1 actions, an S1 action simply gives us a functor from BS1 to spectra in this case, sending the one object of BS1 to THHR. And in this case, well, we can just take the limit. And this limit is usually denoted homotopy fixed points. Right. So our first goal today will be to see what this has to do with HC-, which, if you recall, we defined in terms of a con operator and a certain X group. So in order to make the comparison precise, we'll first make explicit something that we have already seen glimpses of, which is the notion of a stable infinity category. So if you have an infinity category C, it's called stable if C has finite limits and finite colimits. And this is the crucial part, any square ABCD is a push-out if and only if it is a pullback. And another way to think about this is that if you specialize to the case where you have 0 here, this is saying something like co-fiber sequences are also fiber sequences. There are many consequences to this, particularly that suspension and loops are actually inverse equivalences here, so you can just shift objects around. And in particular, many of the examples we've already discussed are stable infinity categories. For example, spectra or the derived category, the full derived category. The bounded derived category doesn't satisfy this. And by bounded, I meant like the dr bigger or equal 0. Right, and so the main feature of stable infinity categories that we'll employ now is the following lemma, namely, if C is stable, then there is a unique lift. And unique means essentially unique. There's a contractible choice of such lifts. From map, the mapping space functor from C op cross C to spaces along the sort of forgetful or loops infinity functor from spectra to spaces. So this lift is denoted map. And when I say unique here, I have to impose a condition, which is that map is exact in both arguments. And what does exact mean? Well, as I mentioned here, in a stable infinity category, co-fiber sequences and fiber sequences are the same. So it makes sense to just require that a functor preserves co-fiber sequences and fiber sequences, right? This is a functor, like if I fix one variable, this is a functor from a stable infinity category to a stable infinity category, and I can just ask this to preserve co-fiber sequences. And that this is equivalent to requiring that it preserves all finite limits and all finite co-limits due to these decomposition tricks where you can express co-limits in terms of push-outs. Yeah. Right. So, in other words, on a stable infinity category, we actually don't just have mapping spaces, we have mapping spectra. And how does the argument go? Well, I'll just give a sketch, because of course you need to say a little bit about functoriality, but I'll just illustrate for you to like how to get a mapping spectrum for two fixed objects. And here the observation is simply, in this stable infinity category C, we can write an object as loops of its suspension, as loops squared of its double suspension, and so on. And so in particular, we can write map xy in terms of this suspension here as this. We can pull out the loops from the second variable because it's a limit. We can also write this as loop squared map x sigma squared y, and so on. And now if you think about this, this exactly gives you a spectrum, right? This is a sequence of spaces with equivalences to loops of the next. So this defines a spectrum. And vice versa, one can check that from the requirements here, your mapping spectrum actually has to look like this. Right, all we've used here, yeah, let me not go into that. So we canonically have these mapping spectra, and one of the main appeals here is that this allows us to write down some of the nice expressions for limits that we had in spaces, also in spectra, by replacing mapping spaces to mapping spectra. So that's what we will use. So what do I mean by that? Well, it turns out that if I is some infinity category, no assumptions, not stable or anything. I guess it should be small. Then first, the functor category from I into spectra is stable. And second, we have a formula expressing the limit over I of a functor f simply as map in the functor category. And this is lowercase map. This is the mapping spectrum in this stable infinity category from the constant S functor, so the functor that takes everything to the sphere spectrum, into F. And I want to leave the proof of this as an exercise. But I'll give you a hint. So the first case, the the first statement is really just related to the fact how you take limits and colimits in functor categories. And for the second fact, recall that this is similar to how we took limits in spaces. Right? In spaces, we said if you have a functor category of diagrams in spaces, then the limit of such a functor is really just maps from the constant point functor into F. So I claim that if you just use the construction for the mapping space I just gave you, you can relate this expression here to the formula we gave in spaces. I think that's a good exercise to get a little bit more fluent with spectra. All right, so what's this comparison that I mentioned earlier to HC minus? So we define TC minus as homotopy fixed points on THH. So the analogous statement here is that HC minus, as we defined it previously, is equivalent to just taking Hochschild homology as an object, or the Hochschild complex as an object of the derived category, which is also stable, by the way, and taking homotopy fixed points on that. So in other words, we get HC minus from HH in the same way that we define TC minus from THH. So what's the idea here? Well, I've mentioned this before, but it's really useful to identify DZ, the derived category of the integers, with modules over HZ, or I suppose, I guess I wrote this like this in the last video, probably. So HC is this Eilenberg-MacLane spectrum, right? So for these connectivity reasons, or because this functor H is like symmetric monoidal, it's an algebra. So you can consider module spectra over it. And it turns out there's an equivalence between these symmetric monoidal infinity categories. So you can kind of think of this as a spectrum with an HC action as well, and then take limits there. So in particular, we can write the Hochschild homology and then homotopy fixed points on that as maps in the functor category. So in the category of spectra with S1 action from S to HHR. So this uses that limits of module spectra are computed underlying, right? This was a statement, this statement here was a statement about taking limits of diagrams in spectra. Now we have a diagram in this category mod HC, but the limit can still be computed by the same formula. This is just asserting that the forgetful functor from modules to spectra preserves limits. So we have this, and this is just, I wrote this const S here. This is still referring to the constant functor, but now I think of this as the spectrum S with the constant S1 action. So I'll just write it as S. Maybe I could put like S triv here, but I'll just write S. So, and now this is maps in spectra, right, in spectra with S1 action, but we have an adjunction between just spectra and HC modules, right? So there's an adjunction similar to how you have this for classical modules, like an induction restriction adjunction. There's an adjunction that tells you that here you can also compute this. Since the target is an HC module, you can also compute this as map from functors BS1 to a mod HC from HZ to HHR, right? And now this is taking place completely in this world of like this mod HZ, which we said as an infinity category also coincides with DZ. So suddenly we are in the world of homological algebra, more or less. We're saying this is the mapping spectrum in objects with S1 action in DZ from just the complex Z concentrated in degree 0 into HHR. And now, if you remember from the video on S1 actions, it turns out that objects with S1 action in DZ can actually be expressed in a nicer way. So we saw that this is the same as just the category of modules over chains on S1, the DGA of singular chains on S1. And then we also saw that as an algebra, this guy is formal. It agrees with just an exterior algebra, which we called A. Right. And now what you have here is a mapping spectrum in just a category of modules over some graded algebra. So this is like I'm writing mod, but this is still modules over this object A in DZ. So this is still some kind of derived category. And similar to how mapping spaces in a derived category compute some Ext, this also has is the complex that computes Ext. So another way to write this maybe is as derived Hom over A CHHR. And this was our definition of HC minus. And a remark I want to make here is that with our original definition, there was some trouble with the multiplicative structure. So we couldn't, like we wrote down an actual complex for this by writing down an explicit resolution, but we had some trouble putting like a strict DGA structure on that. And there is a reason for this, which is that last time we saw that this equivalence here, or I stated that this equivalence doesn't really work on a symmetric monoidal level. It doesn't really, like somehow there are different Hopf algebra structures on chains of S1 and on this A. So what's going on here is that there will be a nice multiplicative structure on these homotopy fixed points. But that simply doesn't correspond to something that you can write down easily algebraically on this side because of this problem that the formality is not one of Hopf algebras. Right. And what's the precise statement about the monoidal structure? Well, I'll just state the ingredients. So first of all, this homotopy fixed points functor is lax symmetric monoidal. And secondly, the S1 action on THHR or HHR is compatible with the product structure on THH or HH that we get that if R is E infinity. Right? If you just plug in an associative algebra, then we saw that THH just gives you a spectrum, no extra structure, or at least no ring structure left. But we saw that if you plug in an E infinity algebra, then THH itself has an E infinity structure. And the claim here is that it's not just a functor from BS1 to spectra where the underlying spectrum also has an algebra structure for a different reason. It really refines to a functor from BS1 to E infinity algebras in that case. And so that tells you, like both of these statements together tell you that there is an E infinity structure on TC minus if R is E infinity, and compatibly on HC minus for an ordinary ring, right? So I'll not prove this. This is a little bit technical maybe. But just as a statement, so we have this straight here, the product structure on this construction through homotopy fixed points and on the corresponding version for THH works. There's a nice coherent E infinity structure. So in some sense, this is also motivation, like even if you only care about the ordinary story. This here already tells you, like, together with the fact that you can't really write this product structure down so easily over A, this maybe suggests that this S1 action perspective is very natural. So now we want to get to actually compute these things. So we have to get some control over how to compute homotopy fixed points. And here the first observation is following lemma. So if we have a spectrum with S1 action, and the underlying spectrum is of the form HA. It's an Eilenberg-MacLane spectrum living in degree 0. Then it turns out the homotopy groups of the S1 fixed points are really easy to describe. They're polynomial on A with T of degree -2. And I guess, right, so maybe, so This A is just some abelian group here. In that case, by writing A adjoint T, I really mean something like A tensor with Z adjoint T, for this to make sense. But it's really just copies of A in every negative even degree. But of course, if the A was a ring, then the HA gets an E-infinity structure, so the homotopy fixed points get an E-infinity structure, and so it makes sense to ask what is the ring structure, and then in that case it's really just the polynomial ring. So this description here is compatible with ring structures. All right, so how do we do this? Well, a priori, giving an S1 action on a spectrum is a really large amount of data. But on Eilenberg-MacLane spectra, it's surprisingly simple. What's going on here? Well, the full subcategory of spectra on all Eilenberg-MacLane spectra and by that I don't mean shifts, I really just mean things of the form HA, so Eilenberg-MacLane spectra in degree 0, so to say. This category is actually discrete, or I should say is a one category, which means that its mapping spaces are all discrete. Right? And what's going on here? Well, if you take the mapping space from HA to HB, then it's actually simply homotopy equivalent to simply Hom AB with the discrete topology. Right, so this is basically one way to think about this is through obstruction theory, right? So HA you can build from cells starting in degree 0, then you need some 1 cells, some 2 cells, and so on. You need cells in all these degrees. But to define a map into HB, since HB has trivial homotopy groups in positive degrees, you only need to define your map on the 0 cells such that certain relations imposed by the 1 cells are satisfied, and then you extend uniquely over all the higher cells inductively. So in other words, you can work out that a map from this to here is simply just given by choosing a homomorphism like this. Or I guess there's a map in this direction which looks at how the map acts on pi 0, and it turns out this obstruction theory perspective tells you that that's actually a homotopy equivalence of mapping spaces. Right, and so a functor from BS1 to SP, which takes the base point of BS1 to HA, actually is constant. Why is that? Well, this guy is connected. And in fact, it's even simply connected, right? So as a space, its pi 0 is just a point, and its pi 1 is also trivial. So if you have a functor from this into a 1 category, namely this full subcategory on Eilenberg-MacLane spectra, it factors through the 1 truncation of this guy, which is 0. Or I guess said differently, to specify a functor out of this infinity groupoid, you have to choose it on the 0 cell, which we did here. But then the next thing that comes into play is a 2 cell. and that already doesn't like if you go into a one category, there are no two morphisms, no non-constant two morphisms, right? So when I say cell, then I'm thinking of this as CP infinity, right? And that has this cell structure with even degree cells. All right. By the way, maybe I should have said that this full subcategory, of course, has a name. It's the category of abelian groups, right? So we see here that this infinity category spectra here has as a full subcategory the category of abelian groups. So said differently here, this data here really boils down to an action of S1 on an abelian group. And then, of course, what are you going to do? You're just like all the points of S1 are in the same connected component, so they have to act by homotopic maps, but the category of abelian groups has discrete mapping spaces. Maybe that's yet another perspective. So, but anyways, this factor is constant, right? So we're not looking at something very general here. We're really asking for the homotopy fixed points of the constant action. And it turns out, this is again similar to what we said about spaces when we defined homotopy fixed points. You can describe the homotopy fixed points here as a mapping spectrum from sigma infinity plus BS1 HA. And I want to pose this as an exercise. I'll give you a hint. You can also write this side very canonically as a limit. All right, so the thing we're computing here though, right, maps out of sigma infinity BS1 to HA. That, it turns out, has homotopy groups given by the cohomology of BS1 with coefficients in A. And that has this description, right? If you remember this BS1, that's really just CP infinity, and the cohomology of that is polynomial as a ring. Right. And the statement that went into this, that's really, remember that we said something about how cohomology is the same as like something like Hn is given by maps from a space into sigma n of HA. So you can get this description by thinking about, by suitably shifting this. So you're talking about a pi 0 and then observing that pi 0 of the mapping spectrum is really pi 0 of the mapping space, because the mapping space is the underlying space of the mapping spectrum. All right, so we understand what's going on for S1 actions on Eilenberg-MacLane spectra. What happens for general spectra? Well, there is a way to decompose a spectrum into Eilenberg-MacLane spectra, namely the Postnikov tower. By just remembering what Eilenberg-MacLane spectra you have there, that's exactly the data contained in knowing the homotopy groups, you lose some information though. You lose how these Eilenberg-MacLane spectra were glued together. And the effect of this on homotopy fixed points is captured in a spectral sequence, the homotopy fixed point spectral sequence. So this is the homotopy fixed point spectral sequence. Let me abbreviate that by AHFPSS in the future. So the statement here, and I'll say some technical words here. So this is a multiplicative, conditionally convergent spectral sequence. And if you don't know what that means, just ignore it. It's some technical things about how this behaves. And it takes the following form. The first page, the E2 page, is given by the homotopy groups of the spectrum X adjoint T. So this kind of looks like our spectrum would simply consist of individual Eilenberg-MacLane spectra, one for each homotopy group. And what it converges to is the actual homotopy groups of the homotopy fixed points. So I'll draw a picture here so we see how to think about this. So this somehow lives only, like this is going to be Serre grading, and the homological Serre grading, in fact. And in that grading, it completely lives in the second quadrant. So you have the homotopy groups here. This is in degree 0. So these are actually on the axis, but I'm drawing them next to it, so it becomes easier to read. And there's a bunch of zeros here. And then here you again have the homotopy groups times T. And then there's a bunch of zeros again, and then you get T squared and so on, right? So in other words, the homotopy groups live kind of on this column, and then you adjoin the T, a polynomial generator T, living in this degree, -2, 0. And in this grading convention, differentials go, the first differential D2 goes 2 to the left, 1 up. The next one will go 3 to the left, 2 up, and so on. And this being multiplicative simply means that there is a ring structure whenever the X was a ring. And in that case, the ring structure on the E2 page will be the obvious one. The ring structure on the E infinity page will be compatible with the ring structure we have on here, right? The E infinity page is the associated graded of a suitable filtration on this guy. And the statement is then that the filtration is multiplicative, and on associated graded, it's compatible with the product structure on the E infinity page. And the product structures on the different pages are related by the fact that the differentials are derivations, and thus they induce a product structure on the next page, on the homology. Okay, so in some sense, we have an approximation to the actual homotopy groups of the homotopy fixed points, which looks as though all these Eilenberg-MacLane spectra that our spectrum is built from are glued together trivially. But then there are differentials, and these differentials somehow are based on information on how these were glued together. So again, I'll give a non-technical proof sketch just so you get a feeling for like where this comes from. And I guess I've mentioned it before, namely, the idea is that we have a tower or filtration of spectra by looking at the connective covers of X. This is actually not what is typically called the Postnikov tower. This is kind of the dual thing, usually called the Whitehead tower, but I mean, it's closely related. In the Postnikov tower, you would take truncations from above. And if we take this tower, it turns out this is a tower of spectra with S1 action. This is due to the fact that this tau bigger equal I is really a functor, right? So if you had a functor from BS1 to spectra, you can just post-compose it. You still have a functor from BS1 to spectra. So all of these has an S1 action, and I can think about what HS1 does to this tower. And I'll get certain spectra, tau bigger equal 0, HS1, tau bigger equal 1, HS1, HS1, and so on. And note, this is not the same as taking homotopy fixed points and then truncating, right? Even if X was just an Eilenberg-MacLane thing, what was I going to say? Right, so for example, if X was an Eilenberg-MacLane thing, then homotopy fixed points of it, as we saw earlier, has all these negative degree homotopy groups, right? It has this T in negative degrees. And so you see that even if like HS1 of something connective is not necessarily connective, right? So this is not the same as taking just the Whitehead tower of homotopy fixed points. But this is kind of better behaved because this will tell us something, which is the following. So here, if you look at this filtration, the associated graded, so by that I mean you just take in from each of these maps, you look at the cofiber. So here the cofiber, for example, would be an Eilenberg-MacLane spectrum on pi 0 of x. The cofiber here would be an Eilenberg-MacLane spectrum on pi 1 of x shifted to degree 1, right? Because these two guys just differ by a single homotopy group in degree 1. And so on. So the associated graded of this filtration here consists of Eilenberg-MacLane spectra, meaning after applying this functor HS1, which commutes with cofiber sequences, because cofiber sequences are also fiber sequences, and HS1 is a limit, so it commutes with limits, we see that here we have H pi 0x HS1, H pi 1x HS1, and so on. So in other words, what we've produced here from this kind of canonical filtration on X, we've produced here a filtration on homotopy fixed points on X, where the associated graded pieces are these homotopy fixed points of the constant S1 action on an Eilenberg-MacLane space, right? We saw that S1 actions on Eilenberg-MacLane space spectra have to be constant. So, and now it's a general fact, and you need some properties of this filtration that I'll not go into. It's complete and exhaustive. So this is actually the co-limit. The limit is 0. And it also has some multiplicative properties. But essentially, whenever you have a filtration on a spectrum, it gives rise to a spectral sequence where the associated graded, the homotopy groups of the associated graded give you the first page, and it converges to somehow tell you something about the homotopy groups of the original spectrum. So there's some machinery going into here and some bookkeeping of degrees. I'll not go into that. The general idea, though, is to take homotopy fixed points off the Whitehead tower. So that's how we get this pattern. And you see that somehow each of the pieces here in the Whitehead tower contributes to exactly one row of this. So somehow this is how this filtration is organized. All right, and we can even say a little bit more about the spectral sequence. Namely, we can identify the first differential. And this will make a little bit clearer how this is, again, related to these more elementary constructions of, for example, HC minus that we gave earlier. And here the idea is that you can still define a kind of con operator in this setting of spectra with S1 action. So an S1 action on X, on a spectrum X, actually gives a map sigma infinity plus S1 tensor X to X. I don't want to go into how exactly. One way to think about this is Morida theory, right? But we defined S1 actions in terms of certain functors, but you can also, it turns out, in spectra, for example, define them as module structures. And what goes into this is that somehow, since S1 is a monoid in spaces and sigma infinity plus is symmetric monoidal, this guy gets a ring structure. And it turns out that S1 actions on spectra are the same as actions by this ring. So I don't want to say more about that. Let's just take this for granted. But here it turns out that this guy is a spectrum that we can kind of understand. So here the idea is that the canonical map sigma infinity plus S1 to sigma infinity plus of the point, which is just the sphere spectrum, splits. Right? I mean, this comes from the map from S1 to the point. You also have a map from the point to S1, and that splits this. So we have a splitting, and this is something you can do for sigma infinity plus of any space, where we write sigma infinity plus S1 as S plus sigma infinity, without the plus, of the pointed space S1. So effectively, this is somehow something like working relative to the base point. And in fact, this guy is then just S1 or sigma S, or however you want to write it. So in other words, kind of the cell structure of S1 splits in the stable world. And in particular, we can ask, like under this action, how does the generator of this guy, the corresponding element in pi 1, how does that act? And what do we get? Well, so we get a map from sigma x, right? That's the same as S1 tensor x. We get a map from this to x just by restricting this action to this summand. And this in particular gives us a map from pi nx to pi n plus 1x. So we will also write this as b. And this is related to the con operator. I'll not prove that, but somehow when you take if you take Hochschild homology and you have the S1 action on there, then you can think of this of Hochschild homology just as a spectrum with Hz action, right? So in particular as a spectrum, so you get an operator like this on its homology. And the other thing you can do is you can construct the classical con operator from this cyclic structure and so on. And it turns out they agree. So this is really a generalization of the con operator. This tells you how to get the con operator back from the S1 action. But there are some quirks here. For example, this is not a differential anymore. The square of this b squared is actually eta times b, where eta is the corresponding element of homotopy groups of the sphere. This doesn't show up in the HZ linear setting because eta is 0 in HZ, but it does show up here. So this is not really a differential, but it's still a generalization of the con operator. And how is it related to the homotopy fixed point spectral sequence? So here's the statement. In the homotopy fixed point spectral sequence, the differential D2 is determined by the following two facts. So D2 of alpha is B alpha times T for alpha in the homotopy groups of X. So this is how it acts on elements of this 0th column, right? You go 1 to the left and 2 to the left and 1 up. The multiplication by T gets you 2 to the left, and then this operator B is how you get up. And you also have to explain how you act on T, and there you act by sending T to eta T squared. Somehow this eta here compensates for the fact that this B was also not a differential. Somehow if you work this out, it all fits together. Right. So and I'll also not prove that, because I mean, of course, you need to input some facts about, say, homotopy fixed points here. But I'll mention that this kind of statement you can usually prove in a kind of universal example, right? And here the universal example will be a free module over this guy. So if you can compute what goes on in the homotopy fixed point spectral sequence of the free module, then that tells you something about all modules, all spectra with S1 action. And in here we're really asking a very concrete question. We're asking, what does D2 do on the generator of the free module in degree 0, right? There's a specific element in pi 0 of sigma infinity plus S1. That's kind of the universal guy. And we're just asking, what's D2 of that? And that lands in a specific group that you can kind of write down a priori. It's something like Z plus Z mod 2. And you just have to work out what element do I hit there. And so you can work out what goes on in the universal example. There's finitely many options. And then from that, one gets this general statement. But of course, in the universal example, one has to still input something. For example, knowledge of homotopy fixed points of the free module, something like that. So I'll not go into that. But what I'll remark here is that this tells you that somehow TC minus behaves a little bit like taking some kind of homology, periodic or kind of half periodic homology with respect to the con operator, right? If you think about how the E2 page looks like, these differentials all are determined by the con operator. In some sense, they're either given by B or B plus eta alternatingly. And so the E3 page is expressible in terms of homology of certain explicit complexes in terms of the con operator. But the difference to what we saw happen in Hochschild homology is that here we now can get interesting higher phenomena, interesting longer differentials. And for example, this class T is also sometimes not a cycle. We'll explore that a little bit more when we talk about TP, the periodic analog of TC minus, which is not actually periodic. It's kind of fun. But for now, what we want to do in the remaining time is we want to actually see what happens in the case of FP. Right? That has been the guiding example where we've computed everything. And so now we'll set out to work out TC minus of FP. And thankfully, we don't have to think about this stuff. too much in that case. Because, let me draw the spectral sequence for you. Since this is homotopy fixed points of an S1 action on THH, the E2 page of my spectral sequence looks like this. So I have a bunch of FPs here. These are the homotopy groups of THH. They're on generators X, X squared, and so on. Here I have this element T, and then I get this kind of two-dimensional grid, which is completely concentrated in even degrees, where we somehow are we're just polynomial on a generator X in this degree and on a generator T in this degree. So if you think about it, every differential goes R to the left and R minus 1 up, so it lowers the total degree by 1. And so in particular, if everything is even, every differential is 0. So this is also the E infinity page. And now the crucial question is, what does this tell us about TC minus? Well, the first observation we make is TC minus 2k for some number k are complete filtered abelian groups with associated graded given by a sequence of FPs. Right? This is just what we read off here. Right? For example, if you wonder about TC minus 0, then you're looking at this diagonal here. This is how the grading works out. And so this E infinity page here tells you there is a filtration on TC minus 0 whose associated graded is this. But note that there are many different filtered abelian groups you can write down whose associated graded looks like this. Right? It has to be complete, so it's going to be some kind of p-complete thing here. But it could be, for example, the p-adix with the filtration by powers of p. That has the property that all the associated graded terms are fp. Could also be just something like a power series ring in one variable, and you filter by powers of that variable. And you could even have some kind of mixed thing where it's a bunch of z mod p to the 5s, which are filtered in a funny way. So that doesn't help us fully, but it does constrain everything a little bit. And also note, of course, that somehow the fact that on the odd diagonals we just have zeros tells us that the odd degree groups vanish. Maybe I should have said that first. That's let me put that here. TC minus 2k plus 1 is 0. All right. So to proceed further, let's name some elements, right? And so what we know already is there's this T here, and it's definitely, like it lives in the associated graded, right? So we can definitely lift it to an element. So we choose T tilde in TC minus in degree minus 2 and X tilde in TC minus in degree 2 lifts of these elements T and X. It's something we can do, but it's non-canonical, right? There's many ways to do that. We just pick some of them. This will have the effect that, for example, the product of T tilde and X tilde is seen in this degree in the associated graded, and it's detected there by this element Tx. And what you also see by looking at the higher degrees here is the next term in the associated gradient is generated by t squared x squared, and so on. So we see here that all the higher filtration terms in this diagonal, in the associated gradient, are actually generated by powers of this tx. And from that it follows, that's the second fact I want to observe, Tc minus 0 Fp to Fp is surjective with kernel generated as an ideal by T tilde x tilde. Right? For example, you can work this out by checking that an element in the kernel, since the map here is the projection to the 0th part of the associated gradient, an element in the kernel is going to be in positive filtration. Let's say it has filtration 1. So it has some non-zero component in the first term in the, 2, I guess, in this case, so here. So it has some non-zero component in this term in the associated gradient, but then I can subtract a suitable multiple of t tilde x tilde in order to make that component vanish. So suddenly it has higher filtration. Then I can subtract a suitable multiple of t tilde x tilde squared to get the next component away, and so on. And because of completeness, that's going to give me a convergent series of powers of t tilde x tildes, which agrees with my element. So, in particular, since the element P is maybe non-zero in here, but certainly 0 in here, it has positive filtration, and it follows that there is a relation of the form P equals A times T tilde X tilde, where A is some number, possibly 0, right? We could be in this characteristic P case, where this is just maybe like a polynomial algebra over Fp on my element T tilde X tilde. And now the final ingredient to decide what this A is, let me put that here as point 3, is that we have a map from THH Fp to HH Fp, which is an iso on tau smaller equal 2. So we get an equivalence between the homotopy fixed points on this truncated THH, which just has pi 0 and pi 2, and the same thing for HH. And if you think all the way back, we already computed HC minus of Fp. And there the crucial idea was we arrived at a similar kind of spectral sequence where we had, instead of polynomial on x, we had divided powers on x. But it's the same x, right? We saw that this is an iso on pi 2. And we saw back then that there is a non-trivial extension in the spectral sequence. And what we checked back then, so we saw in the spectral sequence for HC minus that under suitable choices of T tilde and X tilde, they actually multiply to P. And back then we did check this by thinking about the con operator on the mod P reduction of HHFP. So there's something explicit that went into this. You could also do that on the THH side. Think about the con operator on the mod P reduction. The mod P reduction has Fp's in every degree, so you have a potential for this con operator to appear. that will also give you what we're about to see. But you can, by comparison here, right, for these guys, the homotopy fixed point spectral sequence here just has these two rows. So we have the x and the t and the tx here. And the same thing happens here. This is some kind of truncated version of hc minus, where we just have these two rows. And we saw back in the computation of hc minus that the pi 0 of this guy is simply z mod p squared. That's what went into this. And so up here, we have this relation. It follows that the A actually has to be an element of filtration exactly 0. Because if it had higher filtration, then this A times t tilde x tilde would just be 0 in this truncation. So it would follow that p is 0 in there. But we know that that doesn't happen, right? We know that there is this kind of relation. Or in other words, we knew that this group, pi 0 of this guy, is z mod p squared. So you can kind of detect this A modulo stuff of higher filtration in this truncated version of Hochschild homology. And so it follows that this A is a unit, right? If something in a complete thing is a unit in the 0th filtration, then it's already invertible. Okay. So finally, we see that A is a unit here, and we have, of course, since these groups in TC minus are all p-complete, right? The associated, it's a complete filtration, and the associated graded terms are all p-power torsion. We see that we can write down a map from ZP, or let me say this differently. So since this is a unit, we can modify our choice of x tilde or t tilde, either, for this to, like, for A to be equal to 1, right? So we can assume that our relation over there is actually just saying that t tilde x tilde is p. Both these elements are elements that have filtration bigger or equal 1 in my associated graded, in my filtration, and I'm assuming, or we've seen now that they agree. Right? This is not something you can see from the spectral sequence alone. So once we know that, we get a map where we just take the free ZP algebra on generators x tilde and t tilde. Right? This maps to TC minus just by the assumption, by the observation that this guy is, like, that the groups here are p-complete. Sorry, this maps to the graded ring TC minus star. But we also now know that t tilde x tilde is p. So here it factors through this. And we got a similar description for HC minus, where we had like a divided power generator back then. But here everything becomes nicer, right? So let me state this as a theorem. TC minus Fp is actually isomorphic. The homotopy groups of TC minus are actually isomorphic to this kind of ring. And let me also state as an immediate consequence of that, Tc minus 2k Fp is simply the p-adix generated by x tilde to the k if k is positive, and by t tilde to the minus k if k is negative. So we get this pattern that each of these diagonals assembles to a single Zp generated by the corresponding power of t or the corresponding power of x. And the fact that this agrees is simply the observation that this map here now is an isomorphism on associated gradients if you put a filtration on here, a suitable filtration. If you put the filtration on here where both p and x tilde are in filtration 2 and t tilde is in filtration 0, just as we've seen it has to hold in Tc minus, then this becomes a map of filtered guys, and you can work out that on the associated gradient you've just identified the p with this guy, so the associated gradient is simply Fp polynomial on these two guys, so just as you've seen here. All right, that is everything I wanted to say here. Thank you all for watching, and I will see you next time.